over to Ian to give Sun a quick introduction.
Thanks very much, Charlie. So yes, my name is Ian Raper. I'm one of the co-chairs of the Space University Network that are organising and hosting this series of seminars. And thank you to Charlie, who's the coordinator for the Space University's network. Today we'll be hearing from Chris Pearson from RAL Space, and I'm just going to say a few words about Sun before we do that. And as Charlie has mentioned, feel free to continue introducing yourselves in the chat whilst we go through this first couple of slides. So Space Universities Network covers all universities within the United Kingdom that have any aspect of space-related teaching. And myself, Lucy Bertu from the University of Bristol and Kate Smith from University of Manchester are all co-chairs of the network. And the network is kindly hosted by the University of Bristol, and we receive some funding from the UK Space Agency. We have probably around 90 plus members from nearly 40 organisations across the UK, so we're represented right across the higher education sector in the UK. And the main aims of Space Universities Network is developing skilled graduates, so people, students like yourself, sharing best practice so that we can improve the way that we teach our subjects, making sure that our curricula are relevant, and generally promoting space science and engineering. So this series of talks is part of helping build the understanding of the space sector and developing the skills that you may need or be interested in developing as you move into your careers, hopefully within the space sector. So that's everything I want to say now. So I'll hand back to Charlie.
Great, thank you. So today we're going to hear from Chris. Chris Pearson is an astrophysicist and head of astronomy group at RAL Space. Chris is a PhD doctorate in cosmology from Imperial College London and his research interest in the evolution of galaxies in the universe. He has worked on astronomical galaxy surveys with many major space missions, including 7 years in Japan, working for the Japanese and European space agencies, 3 years in the UK, working for the Canadian Space Agency. Now at RAL Space, Chris is currently working on the ARIEL mission to search for exoplanets, set to launch in 2028. He is also working on the Square Kilometre Array, the largest radio telescope ever built. Chris is a qualified STEM ambassador and regularly goes into schools for space outreach activities. He has worked at major events such as the New Scientist Live, the Big Bang Fair, and the Royal Society Summer Exhibition. Away from his science research, he is a 5th Dan black belt in Taekwondo and is kept busy by teaching his local club of 150 students. The structure of today's webinar will be about a 30-minute talk from Chris, a short interview with him, and then we'll hand over for a live Q&A from you guys. So put your questions in the chat as you think of them, and we'll get around to them as soon as we can. So I'll now hand over to Chris to begin his talk, Aerial and Alien Worlds, Enabling Planetary Science Across Light Years. Cool.
Okay, thanks, Charlie. Share my screen. Okay, so you should better see my screen now.
That's perfect.
Great. Okay, so thanks for inviting me here today. It's very good to see so many people online, also so many people from different universities around the UK and beyond. So I'm going to talk about exoplanets, so planets outside our solar system. And I'm also going to talk a little bit about the ARIEL mission, which is what I'm working on at the moment, which is a mission to characterize the many exoplanets that are being discovered now. So if I start off where we were many years ago, this is 7 classical planets of antiquity, as we call them. And in fact, these 7 heavenly objects included also the Sun and the Moon, as well as the planets Mars, Mercury, Jupiter, Venus, and Saturn. Basically, all the things in the night sky that could be seen easily with the naked eye that moved across the sky. We now know now that there's additions to this original ancient planet club. For example, we had the planet Neptune was discovered in 1846. That was preceded, in fact, in 1781 by the planet Uranus as well, discovered by William Herschel. And the most recent addition for a small period of time, relatively on the cosmic scale, was, of course, Pluto, which was discovered in 1930 by Clyde Tombaugh at the RAL Observatory in Flagstaff, Arizona. So I guess there's many of you are probably old enough, right? So when you were children, perhaps we had 9 planets in the solar system. Pluto was a planet. However, back in 2006, Pluto was kicked out of the Planet Club, being too small, really being dominated by Neptune. And not quite being massive enough to be a planet, and also, of course, us finding many objects like Pluto out towards the edge of the solar system in the in what we call the Kuiper belt. So back in August 2006, there was 9 planets at the meeting of the International Astronomy Union in Prague. We had about almost 500 astronomers got together and voted Pluto out of the Planet Club. So as it stood, there were then 8 planets. However, it stands to reason, if we look up at the night sky, we see lots of stars, we see lots of galaxies, and it's really common sense that we should think that there are other planets orbiting around other stars. So we would ask ourselves, where are these planets? And astronomy went a long time before actually answering that question. In fact, it took us to about 1992 for the first exoplanets to be discovered. Now, these exoplanets were discovered orbiting what we call a pulsar. So a pulsar is a dead star. It's the end of a massive star's life. So very small, very dense, relatively dim stars. Not the sort of star we'd expect to find planets around. However, we did find a trio of planets around such a pulsar in 1992 and in 1994, discovered by Wolfson and Dalfrau. So this really is the start of exoplanet astronomy. But the bigger discovery, the first really major discovery after this was this guy here. This is 51 Pegasi b, and this was the first exoplanet discovered that orbited a sun-like star. So it orbits a sun called 51 Pegasi. That's a very similar size star to our own sun. Now, when we name exoplanets, astronomers being the imaginative folk that we are, we take the name of the star. So in this case, the name of the star is 51 Pegasi, and then we add a B for the first planet discovered. Not an A, because the A we call we would call the parent star here. And if we discover another one, it's going to be 51 Pegasi C, D, E, F, G, H. So we're not naming these planets quite so romantically as we've named the planets in our own solar system, but rather more like a little bit like a telephone directory, unfortunately. So 51 Pegasi b was discovered by Michael Meyer and Didier Queloz in 1995, and it took some time from 1995, but finally this was recognized in 2019, where the exoplanet discoverers shared the Nobel Prize with James Peebles for cosmology. So the wheels do move slow in astronomy, but they do move. So now we know there's planets outside our solar system. Just how many could there be? And we can do a little bit of a back of the envelope calculation. And it's getting towards the end of the week, but a little bit of simple maths, just counting zeros here. So this is a image of the sky here, and in fact, it's an image from the Herschel Space Observatory. And every dot in this image is not a star. Every dot used in this image is actually a galaxy. And if we count them, which I'm not going to do now, I have on good authority, there's about 100,000 galaxies in this in this image. So every dot you see is not a star, it's a galaxy. So it's going to be one of these guys. So in fact, a galaxy contain anywhere upwards from 100 billion stars or more. So every dot on that big picture, you could break down into 100 billion stars. And we could conservatively say that every star, let's just say every star has one planet going around it. And that's very conservative because we know in our own solar system, there's 8 planets, right? This particular image is about 16 moons big. So that's about, the moon on the sky is about the size of your thumb. So that image is about 16 thumbs big on the sky. If we think about the whole sky is about 160,000 moons big. So if you moved your thumb 160,000 times across the sky, you would have enough thumbs to fill up the entire sky there. So we've got our numbers, and it's about 100,000 galaxies times 100 billion stars times about 10,000 patches of sky, because it's 160,000 divided by 16 moons. And that gives us a round number of 100 million planets. Which is a big number. It's apparently it's 100 quintillion if we want to give the number a name. So if you take anything away from this talk tonight, you can say there's at least 100 quintillion planets in the universe, and that's at least because that's under our assumption that every star has only one planet going around it. So if we have 2 planets on average, then we double that number. If we think that every star has a solar system around it, so that 8 planets, then we start going up another order of magnitude. So that's a prediction. We've seen that the planets, they look as though they're quite difficult, right, to detect. It's taken us until the 1990s to find anything outside our own solar system, and you might think it's like finding needles in a haystack. Although once we get going, it's decidedly easier than you may think. And astronomers have developed various methods for detecting exoplanets, and one of the earliest methods was what we call the radial velocity method. And the radial velocity method relies on the fact that both the star and the planet both have mass, so the gravity pulls on each other, and although the planet is much smaller, the planet will cause the star to wobble as it goes around it. And when we look at the light from that star, we see the light from the star having a Doppler shift. So the same way as a police car siren changes as it comes towards you and as it goes away from you, we see the frequency rise and fall. So we can detect planets around other stars if we see this characteristic wobble in the star's light. And historically, this was one of the first very efficient methods to find planets around other stars. It's not the only method. There's also a transit method. Now, this only works if the planet moves in front of its parent star. We see the starlight here is going to drop as some of the starlight is blocked by the planet as it moves in front. So we see the starlight dip a little bit in its brightness as the planet moves around and in front of its parent star. So this is difficult, right? Because stars are big, stars are bright, planets are small, and planets are dim. So the actual drop in the light that we see when the planet passes in front of the star is minute, and also not particularly necessarily stable in terms of what we're measuring. So we need very stable instruments, and we need relatively sensitive instruments to see this transit effect. But this transit method, as we'll see later, has become more or less the main method now for detecting alien worlds. Okay, so there's other methods as well. I mean, what we'd like to do in astronomy, we'd like to do direct imaging. And again, we have this problem with direct imaging that the stars are so bright. We can get around this problem a little bit by putting a block or a coronagraph in front of a star like this. And then once we block out the starlight from a distant star, we'll be able to see its companion star, its companion planet next to it. And that might seem really difficult to do, and indeed it is, but it has been done. And we can see here, this is one example. This is a star with another telephone number, so TYC 8998-76-1, about 300 light years away. 2 planets going around it. So we can see the star up in the top left with the coronagraph around it, and we can see 2 planets that have been revealed once you block out most of the starlight from the large from the sun itself. So these planets they orbit the star quite a way away, about 5 times and 10 times the Earth-Sun distance, but they are detected by direct imaging, which is a very exciting way to we're actually seeing exoplanets now, not just seeing evidence for them. One final method is gravitational microlensing. So again, this relies on a planet moving in between the Earth and its distant star. And although it's a minute effect, the planet can, in fact, contribute to the bending of light as the light travels from a distant object to the Earth. So again, this is a difficult measurement to make, but has been done. And it's also it's a really important method if you want to find planets that don't orbit around their own sun. Some planets are free floating in space, so-called rogue planets, and this microlensing method is a good way to find these type of objects. So we've gone through some of the methods that there are here. So this graph's a little bit out of date. It's 2019, but what it's showing is the number of detected exoplanets as a function of year of discovery, and it's color coded. So along the bottom we've got the discovery year, and along the vertical axis you've got the number of detections, and it's color coded by detection method. And there's the main methods that we saw earlier: the radial velocity, the transits, the microlensing, and the imaging are the most important ones here. And we can see from the graph, exoplanet astronomy really struggled, from the 1990s up until around a little over a decade ago, and almost everything was discovered with these radial velocity methods. And then around a little bit over 10 years ago, this transit discovery methods kicked in, and indeed we can see over the last decade that in fact the transit method has been really successful at discovering new exoplanets. And in fact, this, as I said, this one's a little bit of an old plot. The most recent estimates of discoveries of exoplanets, in fact, as of today, it's actually quite fortunate that this talk we're having today it actually coincides with the 5,000th exoplanet that has been discovered. So over the past few days, we've passed that 5,000 mark. I think it's something like 5,005, I believe, exoplanets that have now been confirmed as discovered, and that's in a total of about 3,700 and odd planetary systems. So we've also found more than one planet going around the same star. So it's a big day today to celebrate 5,000 exoplanets to date now, which is it's a big number. It's a big jump since the 1990s. Some of it's done on the ground. More often than not, though, we have to go into space to do these discoveries. And here we have a rough kind of timeline of the different missions that have been launched to look for exoplanets. On the bottom, we've got a bunch of space telescopes. Some of you are hopefully familiar with, everyone knows the Hubble Space Telescope. I imagine everyone knows James Webb now, given how much it's been in the news. A couple of other ones, Spitzer is an infrared telescope, and Gaia was looking at the stars in the galaxy. And these are not dedicated exoplanet missions, but they do very good exoplanet science. On the top, this list of subjects, this list of suspects on the top here, these are dedicated exoplanet missions. So some of the early ones, we've got COROT, which is a European Space Agency and French one. And then the one I'll talk about in a bit is Kepler, NASA mission. And then we've got TESS, which was launched in 2018 and working now as we speak. Cheops, a European mission, also launched a few years ago. And then we've got 2 planned ones, Pluto and ARIEL. So these will be launched before the end of the decade. So there's a whole fleet up there looking for exoplanets. Probably the most successful of these to date has been Kepler. So Kepler was launched in 2009 and it operated until about 2018, I think. It was a 1 meter telescope. looking at one patch of sky near the constellation of Cygnus, and basically staring at that one area of sky, continuously looking for transits of planets across the face of their parent stars. And this Kepler itself has discovered well over 2,000 exoplanets. It's been an extremely successful mission. It's finished now. It was one of those missions that that died and then was resurrected using very clever engineering from the ground, where one of the gyros on the satellite failed, so it was wobbling too much. And in fact, the guys at NASA, they were using pressure from the sun, so sunlight pressure on the sun shield to keep the satellite steady, which is an amazing piece of engineering. So Kepler's discovered this plot here shows the relative size of the planet to Earth against the orbital period or the year for that planet. And we can see it's discovered a whole host of planets all the way from Earth up to Neptune and Jupiter-sized planets. So it's been very successful in the discovery of exoplanets. Here's another graph. I'm sort of breaking that down now into the types of planets that we found. And the interesting thing here is that we know there's Earth-sized planets out there because you've got an Earth-sized planet in the solar system. We know there's Neptunes, they exist. We know there's Jupiters. We suspect there might be larger planets than Jupiter out there as well. This one here, the green bar, is the surprise one. These super Earths, these were not predicted, not expected in the exoplanet zoo. And these super Earths are anywhere between 1 and 2 Earth radii in size. They're either big rocky planets or they're small Neptune type planets. So these super Earths are a completely new population. In fact, when we look at the distribution of the size relative to Earth, we have the Earth-like planets down here between like 1 and 1.5, and then this other group of planets up here, somewhere between 2 and 3 of these super Earths. So small planets we now know come in 2 sizes, which was a completely new and unexpected discovery. We weren't expecting this second bump. Okay, so we know there's loads of planets around. They come in all different shapes and sizes, and what I'll do is I'll go through some of these now as well. And again, look at this. This is the same diagram as I showed on the previous slide. We can separate these planets into different sort of flavors. Up here we've got these planets that orbit very close to their sun and very big. We call them hot Jupiters. We've got cold gas giants, which are like our own Jupiter and Saturn. Ocean worlds and ice giants are these intermediate-sized planets. Then we get the rocky worlds down here, planets that are very close to their sun, lava worlds, and perhaps some unknown types of planets as well out here. So hot Jupiters, these were relatively common in the early days. These are planets the size of Jupiter that orbit incredibly close to their parent stars. I mean, some of these planets, some of these hot Jupiters whiz around their stars in a matter of days, or in some cases in a couple, in tens of hours. If you compare that with Mercury, that takes well over tens of days to go around the sun. So these things are much closer than Mercury. They whiz round. They must be transient. They can't last long. If they're gas giants, their atmospheres will be burnt off and evaporated away. In fact, that first exoplanet 51 Pegasi b that I talked about earlier, that's actually one of these hot Jupiters. They can grow to incredible sizes as well. I mean, some of them up to like 20 times the size of Jupiter. So it's 20 times, yes, 20 times the size of Jupiter. Yes, so very, very big planets indeed. There's also planets with which go around 2 suns. So we know in the sky there's binary stars. Some of these binary star systems have planets going around them. In fact, some of these binary stars have multiple planets going around them, and these planets can go around one star, or they can in fact orbit both stars at the same time. This one in particular here, this is an artist's impression of Kepler 16b, about 200 light years away in the constellation of Cygnus. So it's one of the Kepler planets, and it's not orbiting 1 but 2 stars. And NASA did this really nice holiday poster program here, and they've done this one of these for Kepler 16b. So the holiday poster here is where your shadow always has company, because if you were on this kind of planet, you'd have two suns in the sky, and you'd have correspondingly two shadows. As is often the case in astronomy, science fiction has beat us to it. And if there's any Star Wars fans out there, they might find Kepler 16 be somewhat familiar as the planet Tatooine in the first Star Wars movie with the two suns in the sky. And this was discovered back in 1977. Okay, so moving on, there's other weird and wonderful worlds out there. We've got a diamond world. This one is 55 Cancri E. This is a super Earth. It's actually almost 9 times the size, almost 9 times the mass of the Earth, with a diameter of about 2 times our own Earth. And it was actually the first super Earth that was discovered. Whizzes around its star in less than a day. So again, it's probably a very hot planet. Now this particular planet is interesting because when astronomers looked at its possible composition, the suggestion is that it's very heavy in carbon. Now, carbon on the surface, is carbon, graphite, for example, but under the surface, as the pressure gets greater, we know that carbon can be forced into diamond. So it's quite a nice notion with 55 Cancri that this planet might actually contain a lot of diamond. In the popular press, it's called the diamond world. When we think about the mass of the planet and the size of the planet, it's probably got about almost 400 quadrillion times the Earth's GDP. So that's about 21 nonillion pounds. That's 21 followed by 30 zeros. So it'd be quite nice if we could, head off to 55 Cancri with a bucket and spade, scoop up some of the surface, and come back rich people as well. It's a little bit too far away for that, unfortunately. So there's also some other weird worlds. There's worlds. This one's HD 1897 33b, and this one here is a huge gas giant that again orbits very close to its host star. Its atmosphere is scorching hot, well over 1,000 degrees Celsius, and it probably if it rains, it's probably going to rain glass sideways in extremely fast howling winds of more than 4,000 miles an hour. So we looked at this planet before and after it disappeared behind its host star as it orbited, and we could deduce some information about the color. And although this is an artist's impression, the assumption is that this planet might be a very deep, nice kind of azure type blue. And so moving on, we have these lava worlds. I did mention these earlier. These are small rocky planets, kind of like sort of Mars, Earth type worlds that orbit again very close to their star. This is Carrot 7b, whizzes round in less than a day, 20 hours. It's about 1.5 times the size of the Earth, so it was the first potential rocky planet to be found. There's very unlikely to be life on it. One side of this planet is probably absolutely boiling hot. The interesting thing is if the planet is tidally locked, so we always have the same face of the planet facing its star all the time, one half might be really hot, the other half might actually be rocky and cold on the other side. So you could build your house on the Terminator line there, and you might be able to get away with living on Carrot 7b, but again, not a nice place to go on holiday. Once again, beaten to us by science fiction, where we had again from Star Wars, the planet Mustafar in the final of the original, the new trilogy. And so again, it's sci-fi leading astronomy as usual. Water worlds as well. This is Gliese 1214b. This is a super Earth, bigger than the Earth, but smaller than the planet Uranus. And we know the way we work out if these worlds are made of water is because if we get an estimate of the size, and if we get an estimate of the mass, we can get an estimate of the density. And we can usually tell if a planet is rocky or if it's gaseous, or perhaps something in between. If it's something in between, there's a possibility that it may be a water world. So it contains a lot less solid material, than our Earth. And this water may be in deep oceans, or it might just be a shallow sea over the entire planet. And I'm going to jump again to science fiction here. This is from the film Interstellar. So this is Planet Miller orbiting the black hole, a surface-wide shallow ocean. So again, one of these water worlds as depicted in film. So we've thought about planets that go around other suns. That it's also possible that planets can exist without a sun, and we call these rogue planets, no host sun. These are often detected by microlensing, that sort of gravitational lensing effect that I showed. It was one of the 4 methods. And again, you would think that these things are really hard to find, but they have been found. There's a free floating planet, as they're sometimes called. So about 9 times the mass of Jupiter, and it was discovered in 2013 by the Pan-STARRS telescope, it's a wide field telescope, looking for almost like blinking the 2 skies together and finding things that move across the sky. So they've certainly been found, and indeed, again, this is an actual image here of that free floating planet that's been discovered. And again, we can have a little joke about this. NASA make these tourist pictures again. So this planet here, where the nightlife never ends because it's always dark. But what we're really interested in here are Earth-like planets, and this is Gliese 581c. It's about 20 light years away. It's an Earth-sized star, and what we're looking for are planets that live in what we call the habitable zone. Now, the habitable zone, sometimes called the Goldilocks zone, is a position a planet is in from its star where water can exist in liquid form. So if you're too close to the sun, your water will evaporate. If you're too far away from the sun, your water will freeze. If you're just right, you can have water in liquid form. So in our solar system, Venus is too hot, Mars is too cold, Earth is just right. And the idea is that if you have water in liquid form, you may have life as well. So everyone gets excited about that. And the excitement really took off in 2015 when we looked at this, the Trappist system. Trappist system with 7 planets named after Belgian beer by astronomers. So we do have a sense of humor sometimes. Seven planets, all in the habitable zone, all in this Goldilocks zone. So again, these planets they could have liquid water on it. This got to the press, of course, and the press did their usual rational response to astronomy discovery. We had the Daily Express saying, shock alien discovery, Trappist 1 planets are habitable to extraterrestrials. Yep, good. Probably a more accurate cartoon there was perhaps the direction of our telescopes pointing out to try and find intelligent life. So the Trappist system, 7 planets going around its parent star. We've got this really nice plot on the right here. This is this transit method. So this is the light from the star, and you can see the light from the star dips for each of these planets that have been discovered. So a really nice example of the transit method, where the light of the star, we see it decrease as the planets move in front of the parent star. So a really good representation of how this works. I wouldn't get too excited about the Trappist system yet, because unfortunately, when we look more closely at it, on the bottom here, we've got our solar system. And if we enlarge this tiny area around the sun, our own sun here, this is where all the Trappist planets sit. Now, the Trappist planets orbit a red dwarf star, which is a lot less powerful, a lot less bright than our sun. So even though they orbit really close, they still live in that temperate zone, that habitable zone of that star. Unfortunately, these red dwarfs also give off quite a lot of radiation. So again, it's probably not life as we know it in the Trappist system. Okay, so that's the introduction to all the different sort of types of planets, exoplanets we might hope to find. So, and I said, today marks the passing the 5,000 planet limit, which is very exciting. But once we've found these planets, what can we do with them? This is where the ARIEL mission comes in. So the ARIEL mission is a European space mission. It's a UK-led space telescope, launched in 2028 or 2029. Depending on the timing. It's about 1 meter in size, and it does spectroscopy from the visible light to the infrared light. It won't go around the Earth. It will orbit in what we call the second Lagrange point, so a gravitational balance point about 1.5 million kilometers away from the Earth. And it's going to look at about 1,000 exoplanets, both rocky and gaseous. It's not going to find them. It's going to look at ones that we've already found. It's going to characterize these exoplanets. So ARIEL is not a washing powder. It's not a Disney princess. It's a space mission. And it has a main mirror with a secondary mirror attached to it. Yep. And then if we spin it around, we put a baffle on so we stop the stray light from coming into the telescope. You spin it around. On the back, we have our instrumentation. So we have one spectrometer. It's made by the French. We have a camera that's provided by the Polish team. And this stuff all sits on top of some radiators because we need to cool the telescope down. And the whole telescope itself will sit on top of what we call the service module here. So ARIEL, it's quite a small mission. It's what we call a medium class mission, and at the moment we're just entering the design phase for ARIEL. So this little graphic here shows a little bit of what ARIEL is going to do. Again, it's going to look at exoplanets that are transiting their parent stars. And as the planet moves across the star, the light from the star will pass through the atmosphere of the planet. So that tiny thin band around the planet will have the starlight passing through it. And we can look at that starlight as it passes through the atmosphere of the planet. And by looking at the spectrum of the starlight as it passes through the atmosphere of the planet, we can find out what the planet atmosphere is made of. So it's a very ingenious way of working out what planet atmospheres are made of. It's been done before in our own solar system. This is the transit of Venus taken by in 2012 by the Japanese Hinode satellite. And in fact, we zoom in, we can see it's this tiny yellow band around the edge of the planet of Venus. And we can do spectroscopy and we can find here that Venus has indeed carbon dioxide, which is not surprising for Venus. But what is perhaps surprising is it has got water in the atmosphere as well. So this is a good example with Venus, what we intend to do with ARIEL for exoplanets. It's difficult to do at the moment. It's been done with Hubble. The problem is Hubble's super sensitive, but it's not super stable. And you need to be stable to do this sort of this sort of work. This is a picture of this is a spectrum of the Trappist system. There's 7 planets, and again you can see there's some hydrogen in the atmospheres of these planets. Maybe some water. I mean, that's up for grabs, really, isn't it? It shows how difficult it is to do this sort of science. So ARIEL is going to take about 1,000 planets in its main survey, and it's going to look at, for example, what planets have clouds, what they're made of, have they got their primordial hydrogen, helium still remaining or not, colors of planets and some refinement of parameters. Then we're going to dig deeper into a deep survey, about 500, look at the main atmospheric components, what they're made of, trace gases, thermal structure, and cloud characterization. And then we're going to hammer like 50 to 100 planets in what we call the benchmark survey. We're going to look at atmospheric circulation. We're also going to look at spatial variability across the face of the planet, and also temporal variability, how the atmosphere changes as it goes around its parent star. So ARIEL is an international mission. It's led by the UK, both on the science side and the technology side. However, it is a multinational mission here. These are just some of the member countries involved. It's ever expanding, and this is taken before lockdown, when everyone could get together. I think the final time the team met in person before lockdown made us all go on Zoom. However, it's exciting now. We are coming out of that, and we are starting to plan our first face-to-face meetings. So I think that brings me to the end of the talk. Just one thing before we finish. If you do want to have a bit of fun with ARIEL, you can play the ARIEL computer game. We have a little ARIEL computer game that a guy at Cardiff made for us called ARIEL Dash. You can point ARIEL towards exoplanets and you can try and discover some chemical elements in the atmosphere of these planets yourself. Okay, and with that, I think I will finish.
Oh, great. Thank you very much, Chris. That was a brilliant overview of exoplanets. So now we're going to ask any questions that the audience can think of. So if you have any questions, just post them in the chat. We have a couple that were sent in advance from previous surveys. Would you be able to tell us a little overview more about your role as head of astronomy group at RAL Space, and give us a bit of insight into what your typical day looks like?
Yeah, sure. So as I said, I'm the head of the astronomy group at RAL Space, and what that basically means is that I have to look after our involvement in any space missions that we're actually involved in at the moment, or space missions that we may want to be involved with in the future. And that doesn't just cover space as well, it also covers ground-based astronomy as well. At the moment, we're also heavily involved with the Square Kilometre Array radio telescope. So it's really, it's almost like looking after a portfolio of projects and making sure they're all running smoothly, and us at RAL Space, whether we're the astronomers or the engineers or the instrument scientists, making sure that we're well embedded and contributing productively to the various things that we're involved in.
Great, thanks. Could you give us a bit of insight into how the industry's changed over the past 15 to 20 years, or from whenever you became interested in it?
Yeah, so I think that the main thing is it's got so much bigger over the last 2 decades or so. I mean, the space industry as a whole, I think is one of, if not the fastest growing industry in the UK. But certainly, say 20 years ago, projects were big, but they tended to be a little bit more self-contained, and I don't want to say not as well organized, but certainly, given the amount of funding that's involved now, everything has to be quite rigorously justified these days, because everything is on such a large international scale. We try, compared to in the past where we had a lot of like small experiments, most of the stuff these days is pretty ambitious. I mean, James Webb is a good example, enormous project. The Square Kilometre Array is going to be the biggest science facility ever built. So I think it's just everything is scaled up, everything's bigger, and the whole community has just grown and enlarged so much. And one of the positive things about that is that you get to, you interact with so many people in so many different countries, which is a really great thing about being in a job like this.
Nice. And where do you see it going in maybe the next sort of 5 or 10 years?
Right. So there's, I suppose that there's the science astronomy perspective on this, and there's the technical the technical perspective. So I do the technical perspective first, because I think we're starting to look at one of the most exciting things about this is we're starting to look a bit further afield for our astronomy, and one of the areas that's receiving a lot of interest at the moment is, can we go to the moon to do astronomy, either on the surface or at the very first instance. There's quite a lot of mission concepts that are looking at going to the dark side of the moon, so to block off the light from the Earth, the light from the sun, and also radio interference. If you're doing radio astronomy, block off the radio interference from the Earth. So technically, there's a lot of projects, including some small like CubeSat projects as well, that are talking about going to the other side of the moon. Scientifically, I think it's coming. But I don't think we're that far off the possibility of actually finding life off the Earth. which would be a absolutely groundbreaking discovery. A couple of years ago, we had the first hints of life on Venus. Now that's still up for grabs. The team that's working on that is still working through the data and trying to rule out any of the other explanations that are possible. There's also space missions that are being planned to go to the Jupiter's moons, in particular Europa, that we know has probably got an enormous undersurface ocean. There's missions that are supposed to fly through the geysers that are coming off those planets, collect the water and look at samples. So again, compared to 10 years ago, where these things were kind of like being laughed at, we are taking these things more serious now, and I do start thinking now it's a matter of time, which would be very exciting.
Yeah, definitely. So we've got a couple of questions in the chat. We have one from Will. He's asked, how can a hot Jupiter form if it's constantly having its atmosphere burnt off?
Yeah, so that's a good question. The answer is that these Jupiters, these gas giants, don't necessarily form really close into their stars. They may form further out, and we think that gas giants may migrate inwards in their solar systems, so that their formation happens in a relatively stable, cool environment, and they slowly migrate inwards, and in the end they're spiraling towards their parent star. Once they're in that spiraling orbit, it's the end of them. I mean, Jupiter's big. There's a lot of gas on Jupiter, so it does take time to blow these atmospheres off and burn these atmospheres off. But eventually, something so close to its parent star is not going to last a great deal of time.
Cool, thanks. So the next question is, why weren't exoplanets with twice the Earth's radius expected?
It's the reason for this, I think, is really a bit of unconscious bias in that we thought that our solar system was a run-of-the-mill model solar system, and that if there were planets going around other stars, then given the same sort of physical conditions, the same sort of family of planets would be formed. So in our solar system, we see terrestrial planets, we see small gas giants like Uranus and Neptune, and we see the big gas giants like Jupiter and Saturn, but we don't have any super Earths in our own solar system. So many of the theories that went into planet formation really concentrate on how you form a solar system like our own solar system. So I think there's a little bit of bias in there from the outset there, that we weren't expecting these objects. And it goes to show that, in fact, our solar system is not a normal. It's not necessarily a normal place. It may not be an average solar system.
Nice. So the next question: how is an exoplanet's mass estimated? So
one of the easiest ways to measure an exoplanet's mass is to look at the wobble in the light, this radial velocity effect as the planet goes around its parent star. Because the bigger the mass of the planet, the more wobble we see in the light due to the Doppler effect from its parent star. So that's how we get the mass. If it transits, we know the size of the planet because the depth of the light dimming. So once we've got the mass from the wobble and the size from the transit, we can actually work out the density as well.
Nice. What are the challenges of getting involved in the space industry, and what are some of the good ways to secure a career in the field of engineering?
So I think the challenges with the space industry, I mean, it's quite a popular career. There's quite a lot of competition for these positions. I think in terms of well placing yourself for engineering, you have to choose the right subjects at university. Again, that doesn't have to be specific. I mean, engineers come in all shapes and sizes as well. And we have engineers at RAL, for example, who are working on modelling or thermal engineering, structural engineering. So a decent engineering degree is fine for it. And then it's really looking for ways to give yourself some practical experience. There's a lot of institutes and also companies who do run graduate schemes. RAL run a graduate scheme where you join it as a graduate, and you will move around some projects, and then at the end of that year you become a staff member at the institute. So there are ways into it, and also if you're not talking about an institute like RAL, there's also places like Airbus which have similar schemes as well.
Okay, that partners quite well with another one of our questions. If you were able to go back in time, what advice would you give your younger self just before starting your career?
Everything's easier in hindsight, I guess. But I mean, when I started my career, I was very much into the science side, astronomy. My degree was in astrophysics, and my PhD was in cosmology. Now, but the path of my career changed a little bit when I started becoming involved in space missions as well, and moved away from just doing the science, so just being the receiver of the data from these telescopes, into actually being part of the team that developed it to launch as well. So I think looking back, knowing where I am now, I would have probably liked to do a little bit more on the engineering side rather than just the pure science side. But again, that's really where I've ended up, which is fine, because it's great to be involved in so many missions. There's lots of astronomers who don't get involved in space missions at all, and they just use the products from these missions to do the science. There is a balance between science and mission engineering, mission operations, and it's difficult to do both. But it's doable. It's doable.
That's great. You've mentioned that stability is really important to make these measurements. How is that being achieved with ARIEL?
So we have quite ARIEL was quite a modest sized telescope, and the difference with ARIEL is that, I mean, that, for example, things like Hubble they're not unstable, but they've been built generally to be as sensitive as possible. So, for example, a larger mirror pushing the detectors to their limits. Where what we've done is from the outset we've built our telescope, we built our instrumentation, we built our electronics for the sole purpose of looking for exoplanets. So we sacrifice the sensitivity, for example, in favor of having a very, very well understood instrument, and that's perhaps more modest, but when launched, we have thoroughly characterized it on the ground, and also we will thoroughly characterize it in orbit, which includes, for example, looking at stars for long periods of time, to try and remove any of these kind of systematic instabilities in the instrument. So we for example might look at a star for 6 hours, and then compare what we see of that star with what we have on the ground, for example, or look for trends in the instrument. And because we understand the star so well, we can disentangle the astronomical signal from any instabilities in our instrument, and then we can go and apply that to stars with exoplanets around them. So the main difference is that we're not trying to do everything. So something like James Webb is going to look at exoplanets, it's going to do a super job, but it's also doing cosmology. So they have a trade-off in their instrumentation between what they want to do with exoplanets and what they want to look, and they want to look back, to the Big Bang. So instruments are developed slightly differently for your different objectives and goals, whereas what we're doing, we're only looking at exoplanets. We're not doing anything else at all. So we're not a jack of all trades like the other telescopes are.
Oh, nice. The exoplanets seem to need to interact with the path of light between the star and the telescope. Would all planets in orbit around a star allow this observation, or are there cases where the orbit of the planet does not pass between this observation line?
Yes, that's a really good observation. So for things like the so it does depend on the angle of the angle of observation. Clearly, for the transit method, you're only going to detect a transiting exoplanet if it moves right in front of its if it moves in front of its star. So if you think of the planet moving in front of its star as, let's say, let's call it an angle of 0 degrees, and then we rotate that through 90 degrees. So now we've got the planet orbiting its star a bit like an egg on a plate, really. Then we're not going to detect that with the transit method. So all of these all these numbers we quote, like the number of exoplanets discovered, the number of exoplanets out there, they're all lower limits, because we know there's going to be, for example, planets that don't cross the face of their star, which we can't see. And in fact, are also going to be very, very difficult to detect, even with the radial velocity method as well. So it's all lower limits. The best way to do it would be by direct imaging. But again, we know that direct imaging is a difficult, very difficult thing to do. Telescopes like James Webb might be able to do it, but again, James Webb's not going to waste its time staring at 20 hours at a star, which may or may not have a planet around it. It's got more important things to do, really, with its time. So again, this is the good thing. It's the interesting about exoplanets that we do find so many of them, and we think probably there's so many out there that every single star in the universe probably has planets going around it, and it's probably more than one planet as well. Whether we see them or not, they're probably there.
And just following on from that, could you give a bit more information into how specifically rogue planets are detected, and do they fill the criteria of their gravitational pull, giving them their own orbit?
So the rogue planets are discovered usually through the microlensing phenomena. So not really so much through not the gravitational pull on their parent star so much, because they haven't got a parent star. But we do know that but what we can do with these is we can discover them through microlensing. The other way we can also discover them is by looking at the same area of sky for a long period of time, because then we would see objects that are moving. If we compare, many images of the sky. So we can do it by microlensing. That's difficult. We can also do it by comparing images, and in fact, this was done last year, in December last year, where something like 80,000 images over 20 years were combined together in one area of sky to try and find these objects. And in fact, about 100 and over 100 of these objects were found in a small area of the sky, just by kind of I don't want to say blinking the images, but effectively blinking the images to see what changes over that period of time. But 80,000 images over 20 years it's a big undertaking. It's quite a phenomenal piece of work there. But it discovered I think it was about 140 or so new Jupiter-sized planets, just free floating planets.
Cool. So we're just running over time, but we've got one last question from a student in Bangladesh, and they're asking, are there any different methods that scientists would use to find life that wouldn't match our ecosystem or genetic structure?
So that's a really good question. The problem with that is that when we look for life, we need to look for signatures of life. Now, the only signature of life that we understand is life as we know on the Earth. So that's mainly carbon based life. The possible discovery of the bacterial life on Venus, for example, is based on what we know of similar organisms on the Earth. The way you look for life on Mars with the rovers on Mars, again, is looking for telltale signs of life that we understand on the Earth. But of course, life may come in different shapes and sizes, and we get into very sort of deep philosophical discussions about can life evolve in other ways than just DNA. So again, it might be RNA based life. It might be silicon based life instead of carbon. So we'd have to know what to look for. I think at the moment, because we really are. This is such a new subject. Almost all of the work is geared towards discovering life that we are familiar with. I mean, there's even some talk, not with the current generation of telescopes, but perhaps the next generation of telescopes in space that are maybe, I don't know, like a 20-meter telescope in space, for example, would be able to look at exoplanet atmospheres and find signs of industrial pollution, for example, in the atmospheres of planets, which is quite an interesting, very interesting method to look. But again, that's industrial pollution on the same sort of scale as what we have on the Earth. So that's assuming that the energy generation, etc., is all the same. So yeah, it's a really good question, and there's a very high probability that alien life wouldn't be like anything like we understand, and therefore we could be looking directly at this thing and we wouldn't even notice because it's so alien.
Cool, thank you very much. I think that's all the questions, and we've just run over slightly, but thank you very much, Chris, for joining us. That was a really great presentation, and you answered all of our questions brilliantly. So thank you very much for giving your time.
Yeah, thanks for inviting me. Yeah.
I'll just add my thanks to that, Chris. So again, another great webinar with a fascinating subject. I've just popped in the chat the link to our little Menti. So if you could if everyone who's attending could just answer 3 simple questions by setting a few sliders, that's all you need to do. That's really helpful feedback for us for organising these. I've also just added in your STFC careers graduate scheme link. So if anyone's interested in understanding how to get onto it or what the requirements are, they can go and have a look on that website.
Thanks.
So thanks very much, Chris, and thanks, Charlie, for hosting us again.